Hi, in the second video we will be talking a little bit about trusses, and we will be modeling an example that represents the type of problem that you'll be dealing with in your course, Computer-Aided Analysis of Infrastructure, taught by Dr. Guner here at the University of Toledo. So let's jump right into our problem. This is the type of problem that represents, in general, the type of exercises we'll be doing. Like using SAP2000, determine the joint displacements, the member axial forces, and the support reactions for this truss here shown below. So we have a simple truss, kind of, with this design here in the middle. So we have 1, 2, 3, 4 nodes and 6 elements. They're equally spaced of 4 meters, both in the vertical and in the horizontal direction. And the properties are the modulus of elasticity of 200,000 MPa or 200 GPa, which is 29,000 KSI. The area of the cross-section of the element is 2,000 square millimeters, which is equivalent to 3.1 square inches. And the forces that are applying in node 4 are 120 kilonewtons in the vertical direction pointing downwards and 80 kilonewtons in the horizontal direction pointing to the east or to the right. All right, what we need to do is show the joint displacements in a table, the member axial forces, and the support reactions, and also print the deflected shape. All right, so let's go to SAP2000. So here, like I showed you in the previous video, we come to the new model. And since our truss is a little bit more complex than the normal truss, we'll be using the grid-only template. We'll also change the units to be more manageable in this problem to newtons, millimeter, and the temperature to be Celsius. But since the information was also given in the customary US units, if you want, you can do it in pounds and inches or kips and inches. Let's select the grid-only template. So here we have to define how many lines we will have in each direction and the spacing between these lines. This will create an equally spaced grid with the spacings we define over here. One thing to keep in mind in SAP is that it considers the z direction to be the gravity direction. So if you want to consider the self-weight of the structure, you have to design your structure, even if it's 2D, considering the z direction upwards or the z direction to be the vertical direction of your structure. So let's go back to our example that we have. So here, our z direction will be the vertical, and we can either do x direction to be the horizontal or y direction. Let's keep x direction to be more simple. So our x direction grid will have 1, 2, 3 lines, spaced 4 meters between each line, and our z grid will have also 1, 2, 3 lines, spaced also 4 meters. Let's go back to our SAP2000, set our number of grid lines in the x direction to 3, and number of grid lines in the z direction also to 3. The spacing is 4 meters or 4,000 millimeters, and same for the z. We don't actually have to worry about the y direction because we won't be modeling anything with it, so we can just hit OK here. And we will see, like I told you in the previous videos, 2 views. The 3D view with the grid in all 3 directions, and the 2D planar view. So by default, the left-hand side is the XY plane view, which is in the structure, the base of the structure, or it can be also on the top, but it's like if you were looking from top to down. So in our case, like I told you, we won't care about the Y direction because we want our structure to have the Z in the vertical direction. So let's go back and click the XZ plane that we care about. Okay, so here we can start to model our structure based on the grid we specify. But before that, like I told you in the previous videos, let's define the materials and cross-sections properties. Starting with the materials, let's go back to the problem and see that we need a material that have a modulus of elasticity of 200 GPa, or this value in KSI. So this is the only thing we care about in our material. So here, like I told you, there are two predefined materials. One for the concrete, one for the steel. We don't care about it, so let's just delete it for convention. Can delete actually this one because it's the predefined one. So let's assign a steel material. Any one, doesn't matter which one you select. Let's rename it, clicking in modify, show material, and rename it to be just like steel material. And we only care about this value over here, which is the modulus of elasticity, which in the Newton millimeter unit system, it's going to be 200,000 to match our 200 GPa in the problem. All right, so we have our material defined. Let's define the cross-section. So the cross-section properties here, it's only given as the area. So we have to create a cross-section that have an area of 2,000 square millimeters. The easiest area to do that is a rectangular area. So we can come here, and there's no rectangular area for steel shapes. So we can come to Other and select a section designer where we can create basically any type of section we want. So now we can name our section. Let's just call it section. Let's select the base material we will be composed of. So steel material we just created. And then we click here on section designer to edit our section. Right here we can create basically any type of section we want. But we just want a simple rectangular section. So we can come here to draw solid shape and then rectangle. Click on the center of the coordinate system just to specify the center of our cross section. And SAP already creates this predefined rectangular section. Let's right click on it and change the height and width to match our area that we have. For 2,000 square millimeters, the height and width of a square section should be 44.72 millimeters. And again, the material is the steel material we just created. Let's click OK. Let's click the full view to maximize it. And we can check our area going to display, show section properties. And we will see that our area is pretty close to 2,000 millimeters square, which will be fine. So let's hit done, click OK. So now we have our section defined here. Now we can go and start to create our element. So we can come to frame our cables. And how we will differentiate between a frame that will consider the moment action and a cable or a just an axial element, which are trusses, it's by coming to the moment releases and selecting pinned instead of continuous. So now that we have that selected, we also, since we only have one defined section, we see that our section we just created, it's already defined. So now we can just go ahead and start drawing it. If you want to match the node numbering with the specified node numbering of the problem, we have to draw the elements in the sequence it is shown here. For example, if we want that to be node 1 and that to be node 2, then we have to create this element from here to here, and then from here to here, and from here to here. That way, we will be created node 1, 2, 3, and 4. This is the easiest way, but you can also come here and draw the nodes by itself before creating the elements. However, to create elements since the beginning is better because it will create the elements and the nodes. So let's do that. So 1, 2, and then 2, 3, and 3, 4. From here, we can create basically from any type we want. So now we want to create this part here, from here, and then from here, here. So we just hit ESC or escape to get out of this node over here, and click again on the tool, and we can come from here to here, and hit escape again, click on the tool, and come here from here. Now, if you want to check that if our nodes are created at the right numbering that we specified on the problem, we can come to the Set Display Options and select the label of the joints and click OK. So here you can see that we have this node as 1, 2, 3, and 4, which is exactly the same as 1, 2, 3, and 4 that we have in our original problem. All right, so the next step is to assign the boundary conditions over here. So let's select the first node and check in the problem what kind of support this is. So in here, we can see that this is a vertical and horizontal displacement support only. So we can come select this node, come to assign, joint, and then restraints. And because we are drawing it in the X and Z coordinate system, the translation 1, which is X, needs to be restrained, and the translation at Z, which is the direction 3, needs to be restrained. So we don't need to restrain the Y direction and none of the other rotations. So we can click OK and see the type of support we specify. Let's check what kind of support is on node number 2. So this is a roller that only restrains the vertical direction. So let's select the node, come to assign joint, restraints, and only restrain the vertical direction, which is the direction 3. All right, so we have a pin and a roller over here. The next step is to define the loads that are going to be applied on node 4, like in our problem. To do that, first, let's create the load patterns. By default, the load pattern is dead, which will consider the self-weight of the structure. If we want to put external loads, we can come and create a different load pattern and call it live, select the live type of loads, and set the self-weight multiplier to 0, because we only want the dead weight of the structure, the self-weight of the structure, to be considered in the dead load pattern. So let's add the new load pattern, click OK, and now we can come and select the node we want to apply the forces, come to assign again, joint loads, because we selected a joint, and apply the forces. Here at the load pattern name that it will be applied, we can select the live load we just created, and we can both select the coordinate system we want to apply the forces. In this case, global, it's more intuitive. So in here, we have 120 kilonewton meters pointing down and 80 kilonewton meters pointing to the right. So in the pointing down would be the Z coordinate direction, and the pointing right would be the X coordinate direction. So if I want the force to be 80 in X, I just come here and put 80,000 newtons, or I can change that to be easier to type 80 kilonewtons. Now to apply the vertical, we come to the Z and put minus 120 kilonewtons and click OK. So here we see that we have 80,000 newtons, because here in this view we still have the units in newtons. We have 80,000 newtons or 80 kilonewtons to the right and 120,000 newtons downwards. Right now we can already run our analysis, but first, like I told you in the previous video, let's come and restrain this analysis to only the degrees of freedom that we have in this problem. Since we draw our structure in the X and Z plane only, we can come here and select this XZ plane button, which will already clear all the degrees of freedom that we don't want in our analysis. So click OK. Now come to this button, Run Analysis, and let's select the load patterns we want to run in our structure. In our case, if you want to see, we don't care about modal anyways, because we're not doing a modal type of analysis. So we can come here and select run or do not run case, and we will see that now it won't run. But if you want to see only the actions that the external loads imposes on this structure, we can come and also do not run the dead load case, and then the results we see will be only regarding to the external load. If we run the dead load, you will see some moments in these elements, although it's a truss and it should be only axial compression loads, but we will see moments because the dead weight of this structure acts as a distributed load on this element. So let's run only the live load of this structure. Let's also save our structure. Let's call just example 1. Oops. Example 1. And save. There's always, okay, that's fine. And now it's running. And here we can see our deflected structure. So let's go back to our problem statement and see what type of results we need to show for this structure. Right here, we see that we have to show the joint displacements of this structure. The easiest way to show these values over here, instead of going to the element itself, we can set up tables that will give us these results pretty easily. So we can come to display, show tables, and here in the analysis results tab, we can select the joint output and select displacement. So select joint displacements and click OK. Here you will see that all the joints we have only 4 joints. The output case, so this is the result only for the live load that we applied. It's a linear elastic, a linear static type of analysis. And here we already see the results for our joints. We have the results in the first coordinate direction, second, third, and then rotations. So what we can do, you can either come here and export the current table to Excel, or you can simply come, copy all this, Ctrl+C, come to a Excel spreadsheet and simply Ctrl+V it. You can get rid of what you don't want. Call this node, this X, Y, and Z, rotation X, rotation Y, rotation in Z, or whatever you like best. And this is the first one. So the second one, for the member axial forces, we can come and do a similar. So we can come here to display tables, show tables, and select the element outputs, frame output, and then table, element forces or frames. Click OK. And here we will see that the only force that our elements take is the axial one, because they are pinned, they don't take shear, torsion, or moment forces in them. So, and here we have that for the first element, we have different stations. So SAP2000 divide each element in different parts called stations to give you the amount of forces that each of these stations are taken. In this case, since it's only axial, the forces are the same for every station. So we can come here, like we did before, copy everything. If your table gets too big, you can simply come to export current table, then to Excel. Come to Excel, paste it here, get rid of the information we don't want, like the position of each station. Get rid of the other forces, types of forces. Get rid of this and this. So this is our axial force. And this is the element that the axial force is working on. So since the axial force is the same for all of them, we can delete all the other points that we don't care and rearrange them. So this is the element. This is the axial force. If you want to specify the type of force, you see that this is positive, this is negative. So this is tension, this is compression, 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 tension, and compression. So if you want to see what are elements 1, 2, 3, 4, 5, and 6, you can come back to SAP2000 and select the labels of each frame, cables, and tendons elements. And go to display and show undeformed shape. And you will see which elements are element 1, 2, 3, 4, 5, and 6. And then you can come to Excel and say that, for example, element 1 is element 1, 2. And then Excel will give you this problem, but you can come and set as text and then 1, 2. And then you can do that for all the other elements. So the next step in our problem is the support reactions tables. For that, we can come to display, show tables, come to the joint output, and then instead of displacement, we can come to reactions, click OK, and come to joint reactions, and it will show you only the joints that are part of a support system. And you can copy that, paste it here, get rid of what you don't want. And that's it. Lastly, we need to print the deflected shape. For that, if you don't have the deflected shape here anymore, you can come to display, show the deformed shape, select the live load that is the only case we ran, and this is the deflected shape you want. You can either print screen the screen and cut the type you want, or you can just select this part using the snipping tool, for example, that comes in Windows, and attach it in your solution. All right, I hope this simple exercise helps you in your own homework and problems for this class. Thank you.